Uh, Chapter 8. What? Why disappear?
มันทันเวลาพอดี
No, already late. I already started.
เราไม่เปิดกันละสวัสดีครับไปเยอะเยอะอย่างที่สุดเองเลย
เต็มบ้างฝักอะไร
Okay, so chapter 8 will be basic concepts in reactor design and ideal reactor models. Okay, so in this chapter, we will look into how to design a reactor. Okay, and there will be a few types of reactor that we're gonna discuss, and then we will focus on ideal models, okay, ideals, okay, because it's simple, okay, we focus on the ideals, okay. And the outline of the class today, first talk about some introduction about the reactor design, and talk about 4 different types of reactors, okay, a batch reactor, continuous stirred tank reactor, semi-batch reactor, and tubular reactor. And then we'll go into the material and energy balances in reactor design. So go back to first year, right? Material balance and energy balance. You already passed that class, so you must have some knowledge, right? So this will be a test, okay? If you still have knowledge. And then we'll start looking at the design analysis for batch reactor. Okay, so we should be able to cover all of this today. That's all the slides I have. So, the one on Tuesday is still being in production. Okay, so chemical reactor is the heart of a chemical process, right? Because in the chemical process, we want to convert a raw materials or feedstock into some kind of products, and that require some chemical reactions. Okay, so chemical reactor is where the reaction happens. So this is the main component in your process, okay? So factors to be considered in reactor selection. First, reaction rate, right? We already know what reaction rate looks like. We discussed about how dependent on temperature the reaction rate is, right? And it also depends on the concentration, right? And then I need to look at the material energy balance, which we will discuss. And then in the real world, we have to look at the economic considerations, like how feasible it is, right, to invest in a certain type of reactors. Also, safety and environmental concerns, right? Because nowadays, safety is the highest priority. We had some accidents before in the eastern seaboard, right? Some kind of explosion, some kind of fire. So some of that came from a reactor, okay? So we try to avoid that, okay? And also environmental considerations. So like we're going green, right? We're going green, so we want to consume less energy, right? And then produce less waste, okay? So that means you have to design a better process to achieve that goal. Okay? And engineering roles is to balance optimal reactor design with practical constraints, okay? So there's some key questions in reactor design that we need to consider, okay? First, what are the feedstock properties and the purification needs, okay? So sometimes we don't usually get the feedstock as pure component, right? It's usually a combination of a lot of compounds. So what does a feedstock look like, and what kind of purity the reactant is in that feedstock, okay? And then what are the production scale and capacity? So that kind of gonna govern like what type of reactor you use, right? So you wanna do like a small, like a production or a large production. So instead of like maybe you produce like 1,000 tons per day, right? Or you want to like produce like 5 kilograms per day or something like that. So that also dictates like which reactor we should use, okay? And the first thing that we need to consider is, will it be a continuous process or batch process, okay? Continuous means like the material keeps flowing in, reaction happens, and then it flows out with some products, okay? That's continuous, okay? And then a batch process is a batch. So it's not continuous. So it's like you have one batch, you let the reaction happens, and then you stop the reaction, and then take everything out, right? So that's the batch process. Then, does this process require catalyst? Okay, we are learn something about catalyst, right? So catalyst can help increase the reaction rate. That means that it could increase your production capacity as well. Okay, and then what are the effects of the catalyst on the product distribution and operating conditions? Okay, usually it will affect the product distribution, so it may favor one product than the other, right? So we need to choose the catalyst wisely. And then what kind of operating condition, temperature and pressure should we operate the reactor at, okay? That also may be required by some certain catalyst, okay? And then another question, what are the optimal operating conditions, okay? So there will be, because the rate depends on temperature, and then concentration depends on pressure, right? So there might be some optimal point that we should operate the reactor. Okay, types of reactors, okay? So this one, they separate by the shape of the reactor, okay? Tank reactors, so it looks like tank, right? So tank reactors has a batch reactors. Batch reactor is a tank with a stirrer, right? A propeller or stirrer to mix the content. Batch reactor, it's operating in batch mode. So no input, no output, right? Only you put it in at the beginning, you stir it, right? You let the reaction proceed, and then you stop at one point and you take everything out, okay? So this is usually used for low production capacity. So you don't want to make a lot of products, just a certain amount of products, but not a lot, okay? But if you need a lot, then we go to continuous stir tank reactor, or CSTR, okay? We're gonna use the short abbreviation a lot, CSTR. So CSTR is the same as batch reactor, a tank with a propeller to mix everything inside. But for CSTR, there will be an inlet and outlet, so it will be a continuous process. So if it's a continuous process, then you can produce more products, right? And then semi-batch, okay? Semi-batch is a hybrid of batch and the continuous, okay? So I think we have the photo here, right? This is the batch reactor, right? A tank with a propeller to mix up, no inlet and outlet, right? And then this CSTR, so same thing. So it's a batch, it's a tank reactor with propeller to mix it up, but have inlet and outlet continuous feed, okay? But semi-batch is that it only has, it's a tank reactor, but only has either the inlet or outlet, not both, okay? Or maybe it's operate differently. For example, here you have a tank reactor, you have some content, like one reactor in there, right? You load one reactor into the tank reactor, and then you start feeding the the second reactants intermittently or slowly. Okay, we will discuss this in chapter 9 because this can control the reaction, the selectivity or the product distribution. Okay, by doing this. Okay, it depends on the rate expression for the various reaction that happens in the reactor. Okay, and then this is a tank reactor, but then it's liquid, right? And you keep feeding some gas into the reactor like continuously. Okay, or you just have the product, the reactant charge inside. Then you make the reaction happens, but then you keep taking out the products. Okay, this usually helps when you have an equilibrium, right? If you take out the products, then the equilibrium shift to the product side, so you can create more products. Okay? So this could be like a membrane reactor, right? Where the product can seep out through the membrane, and then the reaction keeps going. Yes.
So it cannot be homogeneous or it can be.
It's not one.
Can it be homogeneous?
Yes, it can be homogeneous. Yeah, you just like have maybe you keep yes, those are homogeneous, right? Yeah, it's like this is liquid and you feed the liquid. Yeah, but you keep feeding it. This one depends. If it's a membrane, you can remove products in the liquid phase, right? But then if it's the product is gas, then you can remove it easier because there's already a phase separation. Right? So, but we won't focus on the semi-batch too much because it is, wow, you know. No, because this one is not, yeah, it's a bit complicated because like when you do mass balance, the semi-batch has an accumulation term that changes with time, right? And it also has an input and output. So the analysis for the design equation will be a little bit complicated, but we'll see. Let's see if we will touch on that. I will make decision while I make the slides, okay? Okay, so 3 types of tank reactors: batch reactor, CSTR, semi-batch. Okay, we're focusing on the first 2 for sure. Okay, and a tubular reactor. So this reactor is a tube, so a long tube. Okay, so we have a plug flow reactor or PFR. Okay, PFR is an ideal reactor without back mixing and for large scale production. Usually it's just a tube, right? And then once it flows through the tube, then reaction keeps happening. So during its travel, then the reactant gets consumed and converted to products. So as you go along the tube, you start to making more and more products, okay? Or a shell and tube, okay? So it's also a tubular reactor, but this is for better heat transfer. You might have seen this, right, in heat and mass transfer, right? So TMAC code, yeah, there's a stuff in the shell, stuff in the tube, okay? So depending on what type of properties you have for the feed and the feed, then you choose whether the feed goes to the shell or the tube, okay? But we won't talk about that. That's okay. So we go into a little bit more detail, okay? Batch reactor, see, this is cute, I like this. So a tank reactor with propeller, okay? So batch reactor operates in closed mode. That means there's no inlet and outlet, okay? We will load the reactants at the beginning, close the reactor, turn the propeller on, and then once we reach a certain conversion, we stop the propeller, we open the reactor, and unload everything. Okay, so this one is commonly used for small scale production of specialized reaction. Okay, for example, in pharmaceutical, right? You don't need to produce 1,000 ton of Tylenol per day, or maybe you need, I don't know, but maybe some special medicines you need to watch it, monitor it more closely, right? Because you're making the drugs or the medicine. So batch reactors, it's better when you need to monitor the reaction closely, okay? Or you have a specialized reaction that requires some special treatment. So that's what it's used for, okay? The advantage of batch reactors, flexibility, okay? That means one day you can use this reactor for one reaction. The next day you can use this same reactor for different reaction, right? Because you do it in batch, right? Monday you could be it's thinking about maybe a bakery, right? First day, Monday you make croissant. Second day you make baguette. You still use the same reactor, which is the oven, right? So ideal for multi-product processes and varied production, okay? So this is good when you make food, right? And high conversion, because you can let the reaction go as long as you want, right? So you control the time that the reactant spend inside the reactor, okay? So you can let it go as high as you want, okay? Better control, okay? So each batch can be closely monitored and modified because sometimes a different reaction requires a different conditions, okay? Low initial cost because it's just a tank and a propeller, right? So it doesn't require a lot of upfront investment, so it doesn't need to do all the tubing and all the connection for the feed in and out, right? So you have just a tank and then a propeller. Just you do it in the lab, you have a beaker and a magnetic stirrer, and that's it. That's your batch reactor, okay? And batch reactor usually they use for liquid phase reaction or aqueous phase reaction, okay? The gas phase reactions not so well. They don't usually use it. But sometimes they use the batch reactor for gas phase reaction when they want to do the kinetic data analysis, like we did in chapter 3, right? So we do batch reactor to get the concentration versus time data and use that to kind of develop our rate expression. So that's maybe some rare cases that we use it for gas phase reaction. So there's some good things, there's also some bad things, right? Disadvantage of the batch reactor. First, high labor and operational costs. Why? Because you need a manual labor to load the reactor and then you let the reaction goes, right? You stop the reaction, you unload the mixture of reactant and products. But then you need to clean the whole thing. You need to clean the tank, clean the propeller, or if you're making medicine, then you need to disinfect everything, right? So that requires a lot of labor costs and operational costs, okay? And it's non-continuous, so there's some downtime between production of each batch, okay? Limited scale, so base suit for smaller production. Inconsistent, because then if you don't control it well, then batch number 1 and batch number 2 might be different, right? But in contrast, if you operate in continuous mode, everything is in steady state, right? So the quality of the product is consistent, okay? So that's batch reactor. Any question? Sabai. Because no calculation yet. The calculation comes later. So the next one is continuous stir tank reactor. I think this hyphen should be here. Sorry. So CSTR operates continuously, so it's on continuous mode. Okay, and then with perfect mixing. I think the batch reactor has a perfect mixing assumption as well. What do you mean by perfect mixing? Means that the propeller is so good that it makes everything to have the same composition. It's a magic propeller, magic stirrer. Okay, so mix everything. So the whole tank has same composition. That's the perfect mixing assumption. Okay, so it has uniform composition and temperature throughout the reactor. Okay. Commonly used in liquid phase reaction because it has the right here, it looks like liquid, right? Because the gas phase, usually gas phase, we go forward, tubular reactor. Okay. So, but CSTR, there will be an inlet. Okay, so you feed your raw materials here, you let it react, right? And you have some product coming out, right? So when it's steady state, so this thing is going in, this thing coming out, and then nothing changes with time, okay? Because when it's a steady state, it doesn't change with time, right? And you will see that in the mass balance, okay? The advantage of CSTR, uniform product quality, okay? Because we operate in continuous mode, so the product that we get is the same all the time, okay? Unless something happens. Okay? Simple design, easy to control because it operates in the steady state, okay? Can be used in series to improve conversion. We will look at this. So instead of just one big tank, we might have several small tanks connected in series, and that usually improves the conversion. Okay. Then it's suitable for slow reaction requiring longer residence time. Okay. So if the tank is big and the feed is slow, then the residence time means the time that the contents spend inside the reactor. Okay, so if you want it to spend longer, you decrease the flow rate. Okay. Disadvantage of CSTR, it has low conversion per unit volume compared to the plug flow reactor. We will see about that. Okay, why it is like that. Okay, and yeah, larger reactor size needed to achieve desired conversion. Okay, because it has low conversion per unit volume, and then it has potential for side reactions to kind of occur more and more. Okay. So that's CSTR. Two things, two tank reactor, right? Oops, I have so much time. And then semi-batch, okay? Semi-batch is a combination of batch reactor and continuous reactor, okay? So batch plus CSTR, you get semi-batch. Okay. So, like it here, right? So this is a reactor, a tank, right? You have just inlet, right? Or it's a tank, but you have outlet only. Okay, this is semi-batch. Usually, commonly used for reversible reactions. Okay, because if you continuously remove the product, it shifts the equilibrium to the product side. So we make more products. Okay. Or exothermic reactions, okay? That means that reaction that will release heat, we might need to control the input of the reactants to control the amount of reaction that occurs, because that will control the temperature, right? If you let the reaction proceed too quickly, then the temperature rises up too quickly, then it causes explosion, right? So you need to control the addition of the reactants to avoid overheating. Often used in polymerization, fermentation, gas liquid reaction, okay? Where one reactant is in limited supply. Okay? Fermentation, right? Just like a beer. beer. I think they do batch or they do semi-batch. I don't know. I haven't been to the beer factory for so long. Let's go, nah. I need some draft beer. Huh? No, too early. Yeah. No, but only for bio people, right? Or could be for kinetics people. Yeah, kinetics people. But if we go, you have to promise not to throw up in the bus, okay? Because I took many years ago, I was in charge of field trip, right? Took I think the second year student, the Thai program, to Bullot Brewery factory, right? We go there, they come to talk about the process, and they start serving draft beer. A pretty girl going around a tray of draft beer, right there, and then with some snacks, หมูแผ่น and cashew nut. So they drink a lot, and somebody threw up in the bus on the way back to the university. So I asked everyone to clean the bus for the university.
อาจารย์ที่เป็นแฟนก็ได้ทำเป็นเชียร์ด้วยอาจารย์
Yes, of course.
Actually,
Yes, but that's like a conference room, right? They have a draft beer dispenser right there, and they go and then boot. Just like a homecoming night. See, homecoming night. Here, right? We have Chang beer, right? So boot. What? Chang? Huh? No, Chang has different beer, right? They have like export version, yeah. They have different Chang beer, yeah. No, I'm fine. It's free. Yes. Free is everything. Okay. Advantage of semi-batch: better reaction control because we can control how much reaction proceeds by control the addition of the reactant. Okay. Flexibility: it can handle exothermic reactions or the reactions that like a number of reactions that happen at the same time. We call it the parallel reaction. Then if we control the addition of the reactants, then we can control the product distribution. Higher yield, continuous of the feeding of one reactant can help push the equilibrium to the product side, right? And adaptable to gas-liquid reaction, okay? So you have liquid inside the tank, and then you keep feeding the gas, right? What's the disadvantage? Complex operation, okay? Because we need a good control of the reactant addition and reaction conditions, okay? Labor intensive because it's kind of batch reactor, right? So there will be start up, you're loading something inside the tank, and then you start the reaction by maybe adding something else, and then there will be a shutdown, right? After you reach the final conversion that you want, and then there's cleaning between cycles. Okay, so this come from it being like a batch reactor, and then it's non-continuous like per se, so the product output it might not come out like continuously, right? So there might be some downtime, and then there's potential for inconsistent quality. Okay, so that's semi-batch. Okay, we may not discuss it so much, but it's good to know because usually most of the bioreactor would be semi-batch. Okay, you have something, you add nutrients, or you have something, keep feeding the nutrients, right? Or you can ask for the team. Yeah, this morning he's teach, right? Yeah, because I can tell because he's stay overnight last night. Yeah, because I see him posting Instagram story at midnight. And then it's raining here on campus. So no, he lives far. Okay, so next type of reactor is a tubular reactor. Okay, a tubular reactor is a tube that reaction happens inside the tube. Okay, For the tubular reactor, it doesn't require a propeller or mixer. Okay, we use the flow inside the mixing inside the flow in tube to be our mixer. Okay, some also known as plug flow reactor. Okay, we will talk about plug flow condition later. Okay, this is reactor where the reactant flows through a long tube and then the reaction proceeds as it moves along the tube. Okay, the further down the tube, the more reaction proceeds, right? So more products. Okay, so see, reaction happens as you move down the tube. Minimum back mixing. That means that it keeps going forward. It doesn't diffuse backwards. Okay, and the flow behaves like a plug. We'll talk more about the plug later. Okay, a plug's like a slab. Right, a slab. A slab, S-L-A-B, not slab like this, slab like a disc, okay. Used for continuous production in large-scale industrial process, suitable for fast reaction that precise control over time, okay? Because it's just a tube, right? So the controller just control the flow rate, control the feed rate, right? That's it. But if there is some heat involved, then you might need to look at the heat transfer requirements for this type of reactors. Okay. So advantages of the plug flow reactor, you can achieve high conversion. Okay. Especially for fast reaction, it's continuous, so ideal for large scale. The temperature control is operated at steady state, so temperature control is doable. Okay. It's suitable for high pressure, high temperature reactions, okay? Because usually used for gas phase reaction, okay? If you run at high pressure, high temperature, you just need to build a thicker or better material as a tube. That's it, okay? Low back mixing, so there's no mixing in the backward direction, okay? So some disadvantages. It can be complex to design for non-ideal conditions. Okay. So non-ideal conditions sometimes when you have not a plug flow condition. The plug flow is an ideal condition. So if it's not ideal, so it means the velocity profile might not be flat. There will be some back mixing. Then that can lead to variable reaction rates. But then we'll focus on the ideal one, okay? There's potential for hotspot. So hotspot is a spot along the tube that has a higher temperature than normal. Could be from non-ideal mixing, right? Mixing is not so well inside the tube, and then it creates some maybe what do you call? Something that's stuck inside and not moving, okay? So it could be a potential hot spot. Require larger footprints, okay? Because for longer reaction that needs longer time, we just need to increase the length of the tube, right? There's nothing we can do. We need more volume, right, for longer time. So we need longer tube. So if you, for example, you have a 1 kilometer tube, that takes up a lot of space, right? Difficult to maintain because it's a continuous tube. If something is stuck inside, you need to remove that section and clear it, right? So, but then you need to know first where there is deposit inside, and then usually because you don't know it, right? Usually you have to some kind of non-destructive technique, like a X-ray or something, to find out if there's some deposit inside. Because sometimes we have some deposit inside, maybe some carbons or some kind of precipitate. So we need to clean. That's it. The 4 types of reactors. Okay, we will focus on batch reactor first, then tubular reactor or plug flow reactor, and then CSTR. And then we're going to talk about the combination. Okay, we don't use just one, right? One is too simple. We use a number of different reactors connected in series or parallel. So we can look at that too. Okay. Okay. The consideration for reactor design. The first thing, the key tool is material energy balance. Okay. Material balance is always needed, for sure, for reactor design. Energy balance sometimes is required depending on the type of operation you do. Okay. Because we have, I think we will look at this later. There will be some isothermal operations. If you keep everything at the same temperature, right, then there might be some, you might require some heat to be removed or added to the system. Okay. The design challenge is the kinetics of the reaction. So depending on the rate expression for each reaction, so you have to design the reactor based on that, right? Heat transfer requirement. Okay, you're gonna run it as adiabatic, right? You heard adiabatic before, right? Q dot equal to 0. Or you're gonna do like isothermal, we keep the temperature constant. And then mixing efficiency, okay? All that we will discuss is a perfect mixing condition. So perfect means everything is the same. But in real life, no propeller is based like perfect, right? So then you might need to look at some like a non-ideal condition for reactor design. But that's beyond our scope, okay? If you want to learn about that, you can take the graduate course. Apinan and Lungtiwa teaching that. So you learn about non-ideal reactor, right? And then reactor configuration. So you might have like a number of reactors connected in parallel or series. So that you need to design. Okay. Then the temperature control is important because we want optimum reaction rate and safety. Okay. So material balance. Okay. Go back to first year and bring it back here. Okay. Go back thinking about Ajahn Lumtiwa teaching mass balance, right? And bring them back. Okay. But our case, it won't be that complicated. Okay. Very simple. Okay. You have this is a volume element inside the reactor. Okay. You have the reactant enters. You have the reactant leaves with some products, hopefully, and then the mass balance of input equals to output plus disappearance by reaction plus accumulation. Okay. Then we will look at each case of the each type of the reactor, and then we will start from here and we will go somewhere. It will give you like a what we call a design equation for different reactors. Okay. So the flow in and flow out. Okay. We represent both the convection and diffusion of reactant into and out of the volume element. Okay. But mostly it's convection, so it goes with the feed flow, right? Diffusion will be too small. The third time, or the third term. The third term is a product of volume and reaction rate. Okay, why? Because of the input and output, right? It has the unit of mole per second, something like that, right? The flow rate is molar flow rate. It will be mole per time, right? But the reaction rate, right, has unit of mole per volume per time, right? So the third term, which is the disappearance by reaction, that would be you need to multiply the rate of disappearance, which is minus RA, right, with the volume of reactor. Okay, this assuming you have a perfect mixing, like everything inside the tank is the same, right? So rate multiplied by volume, then you get the whole thing. The disappearance would be mole per time, right? If you multiply the rate by volume, so this thing disappears. So you need to, this one will be minus RA, which is the rate of disappearance of the reactant A, right? Multiplied by the volume of this element. Okay? So that's the basic one. Material balance. Then energy balance, okay? This come into play when there's like a heat transfer required. So whereas temperature gradients within the reactor, energy balance will be used in conjunction with material balance. Okay? Energy balance is looks something like this. Okay? So it's over a volume element as well, with an increment of time of delta T. So accumulation energy equals to heat transfer, energy transferred by heat and shaft work. Okay? So this is a Q dot and WS dot, right? Heat transfer, heat and then shaft work. And then also it has energy effects of material coming in and going out, because materials coming in carry some enthalpy, right? It will be enthalpy of materials coming in, and then we have enthalpy of materials leaving, right? So when you have to use both materials energy balance, then it can get complicated, okay? Because when there is an energy balance, you suspect that there might be a change in temperature, right? And a change in temperature would be a change in rate constant according to Arrhenius relation. So it becomes entangled. So you need to solve both simultaneously, okay? When you have a non-isothermal operation for the reactor. But that will be the last chapter, okay? Then the term corresponding to the entry and exit of the materials usually contains enthalpy, right? But there are some other type of energy that it could carry in with it, right? For example, potential energy and kinetic energy, right? Potential from the change in the height, right? And then kinetic energy from the velocity, right? But usually enthalpy would be large compared to potential or kinetic energies. So we usually neglect the potential and kinetic energies, okay? Focus on enthalpy only. And then shaft work, for a tank reactor, shaft work come from the work of the propeller, okay? But compared to the heat transfer, usually the shaft work term is small, then we can neglect them, okay? And then other chemical reaction rate does not appear explicitly. Its effect are reflected in the difference in temperature and composition. Okay? Don't forget the rate, right? First time we have power law. There's a temperature can affect the concentration, right? Because especially in gas phase, the concentration is PA over RT, the partial pressure divided by RT, right? So if the temperature change, concentration can change, right? If concentration change, reaction rate also changes, right? And K, Arrhenius relation, right? So temperature change, the reaction rate constant changes, and so does the reaction rate. Okay, so this depends on temperature already. So even though there's no heat of reaction in the energy balance, but then then the change in the enthalpy that will cover the heat of reaction. Right? So non-isothermal would not be so nice, okay? So maybe you prepare yourself for the worst, okay? Any questions so far? Material balance and energy balance. We will start from the same material balance and then we will apply our assumptions for each case, for batch reactor, for tubular reactor, for CSTRs. And then we will come up with what we call a design equation, which is a starting equation that we will use to design the reactor, okay? And there are a few types of the operation of the reactor that we mentioned before, right? Steady state, this is for continuous reactor, okay? Time invariant conditions, that means everything doesn't change with time, okay? So it doesn't change with time. So if you look at the reactor today, come back tomorrow, everything looks the same, okay? So it's for continuous flow reactors. Transient operation, the condition changes over time, but for example, during the startup or shutdown of the process, okay, you start a new process, you need to do the startup procedure that the change will, it will change with time until you reach a certain point, then it will run smoothly in steady state. Or batch system, that's always a transient condition. So in batch system, it changes with time, right? Because the time is the one that controls the conversion, right? So for batch reactor. Then there's also this type based on heat transfer, okay? Adiabatic, okay? Adiabatic means no heat exchange between the reactor and the surroundings. So Q dot is zero. Q dot is zero, okay? So when you run the adiabatic reaction, the temperature, it will be insulated, right? And then the temperature will change, either go up when it's exothermic or come down when it's endothermic, okay? Usually, you run adiabatic operation when the heat of reaction is not that large, okay? So the change in temperature is not that big, okay? That's when we choose adiabatic operation. I think the guideline is that the temperature should not change more than 10-15%, okay? For isothermal operation, we keep the temperature constant, okay? That means the feed stream, the reactor contents inside the reactor, and the effluent, which is stuff coming out, has the same temperature, right? Inlet, inside, and outlet, same temperature, okay? So we need some kind of heat transfer for this operation, okay? So if it's endothermic, you need to add some heat to it. So you have a steam jacket, right? Jacket, and you feed some steam, and the steam will give some heat to the content, okay? But if it's an exothermic, you will have a coolant running inside the jacket to remove some heat to keep the temperature the same, okay? So at the beginning, we will focus on isothermal operations, okay? Okay, and there will be a couple of terms that you run into when we discuss reactor design, okay? First one is space-time. Not time in space, not space-time. Space-time is the ratio of reactor volume divided by characteristic volumetric flow rate, okay? So volume divided by volumetric flow rate. You have the unit of time, right? You have the volume. space-time is tau, right? Tau is a Greek T, right? So VR divided by V, okay? VR is the volume of the reactor, so it has maybe have a unit of like liter, right? And then V will be maybe liter per minute. You divide this, you get the space-time has a unit of time. That's why I call it space-time, okay? And then, but sometimes the flow rate will change, okay? For example, if temperature change, the flow rate might change, the volumetric flow rate, right? Or sometimes if you have a reaction that has different number of moles on the reactant side or the product side, then you have a change in volume as well. So that will change in flow rate, right? So, but usually we will choose a reference state for the volumetric flow rate to be the condition at the inlet. Okay, that's why I put a little zero here to indicate that it's based on the condition of the inlet. Okay. So space-time. So this, sometimes we will use this as one of the design parameters. Okay, so we don't need to give the exact value of the volume or the volumetric flow rate. We just give you space-time, and you can use this to kind of scale up or down your reactor. Okay, you fix the space-time, and then you change the volume and the volumetric flow rate accordingly to keep the same space-time. Okay. Any question? It's kind of residence time is the time that the content spent inside the reactor, right? So, but residence time or holding time, sometimes it's a little bit different. It could be similar, right? Space-time kind of make it ideal, right? Yeah. So, but residence times, sometimes the tank, some reactant stays a little bit longer, right? It doesn't get mixed properly. So usually in the real reactor you have residence time distribution, right? Some reactant comes out faster, some stay longer, right? So if there's something in here, so there might be something that around here that stays a little bit longer, or something that if you like kind of like do the outlet right here, so you might have a shortcut or something. So that, but it's similar, okay? We will talk about that, touch on that a little bit, residence time. But now it's a space-time. So usually it means that a time that you replace one volume of the reactor, right? If the space-time is 1 hour, that means you replace the whole volume inside the reactor within 1 hour. Then the second term is space velocity, okay? Space velocity is simply the reciprocal of space-time, okay? So, unless stated otherwise, the space velocity is the ratio of volumetric flow rate at the inlet condition as well, divided by the volume, right? So it's a reciprocal of the space-time, so it's the V divided by VR. Okay. So if space-time has a unit of time, space velocity has a unit of per time. Okay. Oh no. Speak too much now. Now we're gonna start looking at the batch reactor, okay? So we start from a batch reactor. Let me remind you, right? It's a tank, right, with some stirrer, okay, and well stirred, perfectly mixed, well mixed, same thing, okay. What it means that the content in here is uniform. in composition and temperature. Okay. So for batch reactor, we're starting from the same material balance equation. There's no input, there's no output, so this term is gone, this term is gone. No input and output. Let it be zero, right? So you have disappearance equal to minus, accumulation equal to disappearance minus, right? So look at the accumulation term, right? D by dt of Na. So usually we do material balance for each species, okay? This one we assume that the reactant is A, okay? So use d by dt of Na. So the change of the number of moles inside the tank per time, okay? So this you can go back to chapter 1, right? You can write the number of moles in terms of extended reaction or fractional conversion, right? Na equal to Na0 plus nu A psi. This is in terms of the extended reaction. So with this, dNA by dt, this term is a constant, so it goes to 0, and then you have nu A d psi by dt. Okay. So this is accumulation term in terms of external reaction. Okay. But usually when we do reactor design, we deal with conversion. Okay. Remember conversion? So FA, okay? So when we deal with conversion, we need to identify the limiting reactant first, okay? If we assume that A is a limiting reactant, so we can deal with FA, okay? If there's one reactant in the reaction, then that is limiting reactant. But if there are more than one, you need to find out which one is limiting, right? Look at the stoichiometry and the initial concentration, and you determine which species is limiting reactant, okay? Then FA would be Na0 minus, speak in now. Na0 minus Na divided by Na0, right? So it's dimensionless. And then has start from 0 to 1. And you rearrange this to get Na equal to Na0, 1 minus Fa. Okay. This expression is for the limiting reactant, right? You rearrange this, you move Na0 to the left hand side of Na0 minus Fa, and then move it here, you get then you have this thing, Na equals to Na0 minus Na0 Fa. You take the derivative of that, you get d by dt of Na to be, the first term again goes to 0, you get minus Na0 dFA by dt. So that would be this one right here. Okay? Any question? Yes. A is a reactant. Yes, A represents reactant species. We use A, simple. It could be anything, it could be any name, but we use A. A is a reactant. Any other question? See, so we still go back and use the old knowledge, yes. Na would be number of moles. C would be concentration, which is number of moles per unit volume. Right? N is mole. C is mole per liter.